Hi, welcome to Lecture 7 of Topic 2, Orbits. Here are your learning intention and success criteria. Please complete the KS table. Pause the video while you complete this. Okay, so looking through here, we can see we've got a couple of knowledge cognitions and a skill cognition. First thing we need to know how to do is what are Kepler's three laws. If you don't know them, you can't recall them. The second knowledge is also a recall. That's just how was this law was derived, which is going to be pretty straightforward. We'll get to that later on. In terms of skill, well, we need to be able to use this equation that we're going to learn about Kepler's third law and doing stuff with orbital bodies. So our final investigation in our topics of motion, or our unit of motion, is going to be the motion of the planets. We're going to go out with grandeur. Now, you may recall from grades 7 or 10 the idea of geocentrism and heliocentrism, whether the sun goes around the Earth or the Earth around the sun. And you perhaps got some explanation about the evidence for the later, that the solar system is heliocentric and the Earth and all the other planets go around the sun. Now, in the mid 1500s, Copernicus published his work proposing this idea that the Earth revolved around the Sun, and then he passed away shortly after. And the book was read by several astronomers before being banned in the early 1600s. And one of the people who read this was Kepler, the old mate here in the photo, and he worked in Prague as the imperial mathematician, which is a pretty cool title. He Kepler took Copernicus's writings and the work of Tycho Brahe that he worked under and came to several conclusions about the motions of the planets, and he published them as his three laws. So let's have a look at Kepler's first law. Copernicus proposed that the Earth and other planets went around the Sun in circles. The problem was the data didn't quite fit. Kepler proposed that instead planets revolve in ellipses with the Sun at one foci. So here, I'll just make sure that this is set to pen. Here we can see one foci, here we can see the other foci. So if the sun might be here, and that's why we've symboled it with a big M for mass, this is the ellipse. Now, the circle only has one foci while an ellipse has two, or another way of thinking about it is that the circle has both foci at the same spot. Now, this diagram we have here is very skewed, like this whole stretched out long ellipse thing here, from this side to this side. Um, that is not accurate to reality. In reality, the ellipse for our planets vary by a very small percentage. They're very close to circles, but we want to make this easy to visualize. So what we need to remember is this. The planets orbit in ellipses, not circles, and the sun is one foci of the ellipse. You must remember that second part as well, that the sun is at one of the foci. If you just stated the first part, you wouldn't get a mark for this. You have to state both of them if a question was asking you to write the three laws of Kepler. Going on to the second one, it's a bit weirder to visualize. The second law says that the movement of a planet traces out the same area in the same amount of time throughout the path of the planet. Now, this is a function of momentum and changing force. So I've got a small explanation here. You don't need to recall this. You don't need to be able to explain this, though, but it is here just to help you wrap your head around the why, and it might clue you in a bit more about it, because you can derive it from the first law if you think about this theory. Visually, the law looks like this. Now we can see, again, the ellipse is very distended, but looking at here, we can see triangle B is very long. Don't know why the right-hand side popped up, but very narrow. Okay, the length here for M and L, don't know why my length vanished. The length here from M to L is very short. While here on triangle A, the height is quite a bit shorter than the height of B, but the length around it, the length from R to S, is quite a bit bigger. Okay. If, however, we worked out the area of A and the area of B, they would be the same. we can understand this by going, well, if it's going far, if this distance here, so using our statements of the laws, our displacement or our distance for RS is obviously a lot bigger than the displacement for ML. We can see that in the picture, but the time for RS, capital RS, sorry, is equal to the time for ML. That's what the law states. So therefore, the velocity for RS must also be bigger than the velocity for ML. And that's the only explanation that allows us to justify this. And it is what we observe. Well, that's what Kepler observed. He observed that the planets move faster when they're closer to the sun, when they're at perihelion, than when they are further from the sun. So this directly matches up observed phenomenon. Okay, so again, we just need to memorize this law. Visualizing it can help as well. Third law, though, this is where the math starts to come in. Now, Kepler's third law describes the mathematical relationship between the orbital period, okay, that's t here. Remember, capital T is a special time, a period, the length of one full revolution, the length of swinging backwards and forwards, something like that, or anything like that. So the relationship between the orbital period of a planet and the average radius from the sun. So while they do get closer and further away, this R is going to be the average. We're not going to ask you to work out different value, using the closest and the furthest and taking the average or anything like that. It'll always just give you the average. Um, the ratio of these, period squared over r cubed, is equal to some constant k. All right. Now, that is the same for every object in an orbiting system. Now, this term orbiting system is important. Kepler derived this law by looking at the solar system, and so we've been talking about our star and planets. Mars, Earth, Mercury, Venus, Jupiter, Saturn, etc., etc. But it's also true for planet-moon systems, Earth and its moon, Mars and its two moons, Phobos and Deimos, Jupiter and its dozens of moons, like 80ish, I think. Doesn't matter what system it is. We'll look at one of those in a second, or a planet and a satellite. All we need is a large central body being orbited by another smaller body under the power of gravity. It has to just be gravity. Okay. Now the constant will be the same for any object in just that system, but the K value for the Earth system, so the Earth and the Moon or Earth and its satellites, is going to be a different K number from the Sun and its satellites, its planets, or Jupiter and its moons. But it'll always be constant within a system. Okay, let's have a look at the next page because I've got several examples. Oops, sorry, I forgot about that. Here from the textbook, we can see here taking the radius and the period of revolution for all the planets in our solar system, we get a pretty similar number. Okay, varies by what, about 0.3 across all of the numbers there. So you can see they are very close. Note they're not exactly the same, and that's because the planets do affect each other. So orbits are not consistent, and over time, things do vary a little bit, but the numbers are going to be very close to each other. So let's do some examples. Here we have a moon planet system. We've got Triton and Nereid, two moons of Neptune. We've got there Triton being a certain distance, a period of this, and Nereid is that distance and a period of this. Determine if the data is consistent with Kepler's third law. And what we mean by this is that the t squared, or the t of Triton squared, over the radius of Triton cubed, equaling k, should be pretty close to the period of Nereid squared over the radius of Nereid cubed. Now, one thing to note, we are told that Neptune has a radius of this, so we are going to have to use that radius as well for both Triton, because we can see 24,000 is going to affect at the first decimal point here. And while it will affect a little bit lower on Nereid, it because we're doing it to one, we should do it to the other. So let's work out our two radiuses first. Radius of Triton is 353,000 plus 24750, which will give us 0577773. A lot of sevens. The radius of Nereid is equal to 5560,000 plus 24750 0574855. So now if we plug and play into this, we're going to get that. Now, actually, sorry, one thing I forgot to say. Because we're looking just the ratio of these, as long as these two numbers have the same units, and these two numbers have the same units, we're good. We don't need to do any conversion, because converting, kilometers and meters, not terrible, but converting 359 Earth days into seconds would suck. I mean, it wouldn't suck. It's not hard to do, but the numbers would just be ridiculously large. So let's not hate ourselves too much. All right, so looking at this, we can start plugging things in. The period for Triton was 5.87 squared over, radius of Triton was 377,750 cubed. That equals, okay, and that equals the period of Nereid was 359.9 squared over 5584750 cubed. So I need to put both of those sides into my calculator, and then we will have an answer. So on the left-hand side for Triton, we get, oops, it went forward, apologies. We get 6.39 times 10 to the negative 16. And on the right-hand side, we get about 7.346 times 10 to the negative 16. Now, maybe going, nah, they're not the same, sir, so it's not wrong. 10 to the 16, 10 to the 16. We're looking at powers. When you're dealing with astronomical stuff, generally, if things are within the same power range, you're basically saying they're identical. They're basically the same at that point. The other reason that this is not going to be identical is that, remember, these are moons. They are getting pulled by both Neptune and the Sun. They're getting pulled by other moons inside that orbit as well. So you generally will not get numbers that are identically perfect. The exam from QCAA, if there's any questions involving this, might give you questions that are they're going to have really similar data, but it's probably more that if they do, that they'll give you a question similar to this where it'll be different, and you'll have to justify why it's still appropriate to say that that the data is consistent with Kepler's third law. So in this case, we're just saying it's consistent because the numbers are close enough. Okay, let's have a look at the next one. Here we have a satellite and Earth system. So, oops, sorry. Satellite launched around Earth, knowing the natural satellite of Earth, the Moon, has a period of 28 days and an orbiting radius of 3.8 times 10 to the 8. Calculate the desired radius for the artificial satellite, so it has a period of 1 day. Now, the thing you'll notice is that the radius of the Earth has not been given to us. And if you go to your formula booklet, the radius of the Earth is not given to you there either. So there's a really useful rule of thumb. If the radius of a planet is not given to you, you don't need to use it. If it is given to you, however, you might need to have a bit of a consideration about whether it's something you need to use. So let's identify our values here. We have the period of the moon was 28, and I'm just going to leave it in days. And the period of the satellite is equal to 1 day. And so we can see it's the same unit. So, hey, we don't need to convert, which is great. The radius of the moon is equal to 3.8 times 10 to the 8 meters. And we're trying to work out the radius of the satellite. So first off, I'm just going to write this. T squared over r, oh sorry, T of the moon squared over radius of the moon cubed will equal K, which will equal the things. I'm just going to ignore the K for now. Period of the satellite squared over the radius of the satellite cubed. Now, let's just look at this for a second. 28 squared over 3.8 times 10 to the 8 cubed is going to be a very small number. And over here, we're going to have 1 over that. Well, let's make our life a little bit easier. We can quite easily rewrite this as radius cubed over period squared equals radius of satellite cubed. R, even worse R than before. Radius over period of the satellite squared. This is perfectly fine to do. You can flip things around like this. You just may have to make sure you flip around both sides of the equation whenever you're doing that. So if you are uncertain about why that's okay, maybe don't do it or come and see me. Let's do some substituting. So our radius is going to be 3.8 times 10 to the 8 cubed divided by 28 squared. That's going to equal RS cubed over 1 squared. So that's just going to vanish. So therefore, our radius of our satellite would equal 3.8 times 10 to the 8. The whole thing is cubed over 28 squared. And we are going to take the cubic root of this. Let's go plug that in. And we get about 4.1 times 10 to the 7. It's about 41,000 kilometers. All right. So if we want a satellite that spins around the Earth once per day, we need to put it about that far away. All right, let's have a look at deriving this law. What you need to remember, this is all that's in the syllabus, is that Kepler's third law can be derived from Newton's law of gravitation and the circular force equation. So Newton's law of gravitation we covered in 1.2.6, and it's down there, big G times the product of the two masses of the two objects and divided by the radius squared. And the centripetal force equation, which we covered in 1.2.4 and 5, we see mass times velocity squared over radius. Okay, and we can take this and then derive a better form of Kepler's third law in terms of actually using numbers instead. So let's have a go at that. Starting with our start point, that the force of gravity is equal to G little m big M over radius squared, and the centripetal force is equal to m v squared over r. Well, what Kepler said and what Newton said down the track was that, hey, the force of gravity, because remember, Newton came after Kepler, is equal to the centripetal force. So therefore we can say that this G little m big M over r squared equals little m v squared over r. And taking a look at this, we can see, okay, the mass of the planet and the planet that it's orbiting, well, the mass cancels, the radius cancels, and one of the radius will cancel over here. And I'm going to put everything onto one line to make our next substitution a bit easier. So we get gravitational constant times the mass of the sun, the thing at the center of the orbiting system, equals v squared times r. Now, one other formula that we have, well, if I draw something going around in a circle, well, velocity, the speed of a circle, equals velocity of anything equals displacement over time. But when we're dealing with a circle, the displacement or the distance that it travels is 2 pi r. I know the velocity, I know the displacement is 0 because it's coming back to where it starts, but what I'm really wanting here is the idea of the distance, the linear amount of distance that it travels. And the time that it does this in is called the period. And hey, we need that period to get to Kepler's third law. So now we can substitute that into this and get that Gm equals 2 pi r squared, because this square is still here, times r divided by t squared. Okay, so that 2 pi r goes on the top and the t squared goes on the bottom. So now let's expand that out and we get Gm equals 2 squared pi squared times r squared times r over t squared. Or that if we simplify that, that Gm will equal 4 pi squared r cubed over t squared. Now the rearrangement that it gives us is this. I was so close to not running out of, not going over the top of it. Let me get rid of some of this here. So the final rearrangement and the thing that's given to you in your formula booklet looks like this: t squared over r cubed equals 4 pi squared over g times m. Now g is, remember, a constant. It's in your formula booklet. This big M here in this case is the mass of whatever's at the center of the system. So if we're dealing with the planets going around the sun, this capital M would be the mass of the sun. If we're dealing with things going around the Earth, such as satellites or the moon, the M is going to be the mass of the Earth. If we're dealing with things going around another planet, the M would be the mass of the planet. Now, the only one that you're expected to remember is in your formula booklet is the mass of the Earth. So that's what we're going to use. Satellite moves in a circular orbit around Earth at an altitude of this. The radius of the Earth is this. Determine the satellite. Now we've been given the radius, and we can see there, this is a good way to think about it. This, excuse me, and this are really close. So that means we're going to have to use this to add them together. So our radius is going to equal 4690 plus 6378. So 8, 6 carry the 1. That's going to be 10 carry the 1. That's going to be 11. So here is our radius. We're trying to work out the period. So t is our unknown. And we're told it's about the Earth. So if I head over to my formula booklet, I get that the mass of the Earth, where was it? There it is. The mass of mass is equal to 5.97 times 10 to the 24, and I'll write down G while I'm at it and looking at it, 6.67 times 10 to the negative 11. All right. So now, if we go back to Kepler's law, we know that t squared over r cubed equals 4 pi squared over gm. Now, because I'm trying to solve for period, I'm just going to leave it like this. If I was trying to solve for radius, I'd be cheeky and go radius cubed over t squared equals gm over 4 pi squared. You will honestly see both forms of this equation online equally valid. They're both valid, they're both the same, but you'll see them both written a fair amount of similar times. Let's plug some numbers in. So t squared over 11068 cubed equals 4 pi squared over 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. Ugh, long bit at the bottom. And we can plug all that into a calculator. So I will bring this to the other side so it's multiplied, then take the square root of everything after I've done it. Okay, I will write out the working out just to make things clearer for people. Times 11068 cubed all over 6.67 times 10 to the negative 11 times 5.99 times 10 to the 24. And all of that is going to be square rooted. So go plug that in. We get an answer that is about 11597 seconds. I don't have a context frame for that. So while for this it hasn't asked for it to be in any particular unit, so it doesn't matter. But if on a QCAA exam, a question like this, it would probably ask you to put it into a particular unit. So do be careful and read the box at the bottom to make sure you're doing the right units at the end. Well, we've got it in seconds, divide by 60, divide by 60. We will get a bit over 3.2 hours, which is a lot easier for us to visualize in our head. All right. Now, the second part is asking for the velocity. I'm just going to do that very quickly over here. The velocity for something going around a circle, remember, was 2 pi r over the period. Well, that's 2 times pi times 11068 divided by that 11597. Don't forget that that still has to be in SI units, and that's pretty close to 6,000 meters per second. So we've seen now using Kepler's third law in a more mathematical sense. All right, so looking at here what we've learned this video, we've learned what Kepler's 3 laws are. We've applied that third law to gravitational orbiting systems. And we've seen how Kepler's third law was derived from two laws that we've already seen, the law of gravitation and the law of circular motion. For your entrance to class, please complete questions 1, 2, 5, and 8 to 11 from chapter 5.1, Check Your Learning. Remember that that's from the Unit 3 for text. Copy your answers into the, this is the first time recording this, the 1.2.7 Check Your Learning quiz on QLearn now. So thank you very much for listening. Have a great evening. Bye.